Welcome to this mini course on the set packing and set covering problem. My name is Bertrand Guenin. I'm a faculty in the Department of Combinatorics and Optimization at the University of Waterloo in Waterloo, Ontario, Canada. In the first part of the course, I will give you a brief introduction on the area. In particular, I will tell you what the set packing and the set covering problems are, and we will see three key notions: the notion of perfection, the notion of idealness, and the Mangerian property. Perfection has to do with the set packing problem, and idealness and the Mangerian property have to do with the set covering problem. And then we will have three lectures, each on one of these properties. So one for perfection, one for idealness, and one for the Mangerian property. Note that these lectures will not all be of equal length. So with no further ado, let's get started with the introduction. The set packing problem. So let me start with a classical problem on partially ordered set. So what's a poset? It's a pair, V, where V is a set of elements, and then an ordered relation that satisfies the following three properties. So every element is smaller or equal to itself. If A is smaller or equal to B and B is smaller or equal to A, then in fact A is equal to B. And finally, we have transitivity, namely, if A is smaller than or equal to B and B is smaller than or equal to C, then in fact A is smaller or equal to C. Now, we define two elements to be comparable if one is smaller or equal to the other, and two elements are incomparable otherwise. And the key definitions for posets in our case are going to be the notion of chains and antichain. So a chain is a set of comparable elements, and an antichain is a set of incomparable elements. So pairwise incomparable elements. And so you may ask the following question: what is the maximum size of an antichain in a poset? So let's look at an example. Suppose that I tell you that I can find k chains that are covering the elements of my poset. Now, every antichain is going to intersect each of those k chains in at most one element. So my antichain is going to have size at most k. So if I happen to have an antichain that has size k, then it is a maximum size antichain. And Dilworth's theorem tells you that you can always certify this maximum size of an antichain in that way, namely the maximum size of an antichain is always equal to the minimum number of chains needed to cover the ground set. And we illustrate this on the following posets here. So the points correspond to the element of the poset, and if you have a point above another one which is connected by a line, then that point is greater than or equal to the point at the bottom. So if you look at the red points form a chain, and so do the blue points, and so do the green points. So you have three pairwise disjoint chains. On the other hand, you have an antichain which corresponds to the 3 points in a rectangle there. So Dilworth's theorem is an example of a max-min relationship. And I'll tell you later why you should think of it as a max-min and not as a min-max relationship. And that should remind you of something from optimization, namely duality. So let's just switch gear and think of integer programs and linear programs. So we pick a 0-1 matrix, and by a 0-1 matrix, we just mean a matrix where all the entries are either 0 or 1. And we pick some weights for the objective function, so non-negative weights. And we define the set packing integer program as maximize W transpose X subject to mx smaller than or equal to the vector of all 1. Then we have non-negativity, and then we have the integer constraints. Now note that the condition that x is integer can just be replaced by the condition that all the variables have to take either value 0 or 1. So why the name? Why is this called set packing? Well, think of the 0-1 matrix M in the following way. Every column corresponds to the incident vector of a set. And if I look at a feasible solution to that set packing problem, I'm setting some variables to 1. It corresponds to selecting a number of sets from a family of sets. So what I'm really looking for is a maximum weight family of disjoint sets. Hence the name set packing integer program. All right, so here's our friend, the set packing integer program. And now let me write down the linear programming relaxation. So I just toss away the condition that the variable should take an integer value. And then I take the linear programming dual, right? So now I'm going to have a variable y for every row of m. And then I'm adding integer condition to the dual problem. Right? So the original problem, I call that IP, the LP relaxation P, its dual D, and then ID is what I get from the dual by adding the integer conditions. And now let's just look at the optimal values for each of those 4 problems there. You have the following relationship between those values. So ZIP here represents the optimal value to IP, ZP the optimal value to P, ZD to D, and ZID to ID. And ZIP is going to be smaller than or equal to ZP because I'm looking at a maximization problem, and if I relax the problem, the value of the objective function can go up only. Then ZP is equal to ZD, this is just because of strong duality. And then finally, ZD is smaller than or equal to ZID because I'm adding an extra condition, so we have no minimization problem and the objective value can only go up. Now you should probably spend a few seconds thinking of why I'm thinking of each of those problems as having an optimal solution. All right, so now let's go back to Dilworth's theorem. And let us try to restate this theorem in a context of integer programming. So for this, we'll need to construct a matrix which captures the information from our partially ordered set. So the columns of our matrix will be the element of the poset, and the rows will be the characteristic vector of the maximal chain. So let's just do an example so we understand what's going on here. So here you have elements 1 through 6, which corresponds to the columns. And you have the chain 1, 2, and 5, for instance. So I have the corresponding row with entry with a 1 in position 1, 2, and 5. By the way, I will use the convention that if I don't write anything for an entry for a matrix, it is going to be 0. Right? Because we'll just deal with 0-1 matrices. All right, so now we have this matrix M, which is constructed from the poset. What does our integer program, the maximum, the set packing integer program say for the case when the objective function is all 1. Right, so let's just write down that integer program, maximize 1 transpose x, then I have my matrix M times x smaller than or equal to the vector of all 1, non-negativity, integer conditions. Okay, so as before, you can think of the variables as taking value either 0 or 1. And now look at each of the rows of the matrix M. Those corresponds to your constraint. Well, those rows correspond to the characteristic vectors of a chain. And so the condition will say that you should pick at most one element from every chain. So what you end up doing is picking an antichain, and you're picking an antichain of maximum size, right? So the set packing problem is just computing a maximum size antichain. All right, now let's just look at what happens to the dual problem where we add the condition that the variable should take integer values. Again, for integer cost, right? So what is that optimization problem? Minimize 1 transpose y. And here we're taking M transpose, right? So now I have a variable y for every column of the matrix, so namely for every chain, right? And again, you can think of the variable y as taking values 0 and 1, because the right-hand side is just a vector of all 1. So what you're doing is you're looking for a set of columns that are covering your right-hand side, or equivalently, you're looking for a set of chains that are covering the ground set. So your dual problem is finding a minimum set of chains covering the element of your poset. So if you put those two things together, you realize that Dilworth's theorem is just a statement that ZIP is equal to ZID for the cost vector, which is a vector of all 1. By the way, as an exercise, you should check that, in fact, you have this max-min relationship for every integer cost vector there, and you should think of what it says in terms of partially ordered set. So I would like to look at 3 questions which pertain to this max-min integer programming relationship we've seen earlier. So here are the 4 optimization problems we looked at before, and this was the relationship we had between the optimal value for those optimization problems for any objective function W. So I want to ask the following 3 questions. For what class of matrices does ZIP is equal to ZID for all non-negative integer W? For what class of matrices do I have ZIP is equal to ZP? Again, for all non-negative integer W. And finally, for what class of 0, 1 matrices do I have ZID is equal to ZD for all choice of integer non-negative W? So it looks like we have 3 different questions. In fact, later on we'll see that all of those questions are equivalent, but before we can get there, we need to do a little bit of review of polyhedral theory. So for the first proposition, I'm going to look at a polyhedron P, where P is a set of all non-negative x that satisfy the system of inequality Ax smaller than or equal to B. That polyhedron P is living in Rn, and I'm going to give you 4 equivalent statements for that polyhedron. So the first statement says that P is equal to the convex hull of P intersection Zn. In other words, you take P, you intersect it with the integer lattice, and you take the smallest convex set that contains all of those points there. This is always going to give you something which is smaller, which is contained in P, but the point is that the condition here says that you in fact get exactly P. The second condition says that every extreme point of P is integral. So a point of P is an extreme point if there is no, you cannot express it as a proper convex combination of two other points in P. The third condition says that if you have a point which is in P and you look at all the tight constraints and the rank of those tight constraints is equal to the dimension, namely n, then x bar should be, that point should be integer again. And the last condition says that if you take your polyhedron P and you optimize over it using some integer objective function, every time the maximum exists, then you should actually get an integer value for that maximum. Right? It doesn't say anything about the solution being integer, it just says that the value should be integer. So those four conditions are all equivalent, and we say that the polyhedron P is integral when one or respectively all of those conditions are satisfied. Now we'll see that the last condition is going to be particularly important for us. And we'll see this in just a second. So now let's look at a primal dual pair of linear program. You have this maximization problem P and this minimization problem D. And a key definition is that of a totally dual integral TDI systems of inequality. So AX smaller than or equal to BX non-negative is TDI if for every integer W where the problem D has an optimal solution, then in fact it has an optimal solution that is integer. Right? So I can find a Y that is an integer Y. Now, this is a property of systems of inequality, not of polyhedra. And one way to see that is to notice that this definition of TDI-ness is not invariant under rescaling your system of inequality. All right, so how does this tie in with the notion of integrality? Well, it ties in because of the following result. So you give me a TDI system, AX smaller than or equal to BX non-negative, and in addition you tell me that B is integer. So in particular, you can't rescale it if you want to keep that B integer property, preserve it. Then I claim that this implies that the corresponding polyhedron is going to be integral. And this is actually easy to see from the previous proposition. So what are you going to do? Well, pick a cost W, which is integer, and look at your maximization problem and your minimization problem. So this was your problem P and D from the previous page, right? And assume that the maximum, respectively the minimum, exist, and denote by Z star that value there, right? So I claim that Z star is always going to be integer, which is going to be enough to certify that my polyhedron is integral. So why is Z star always integral? Well, my system AX smaller than or equal to BX non-negative is TDI, which means that there exists an optimal solution Y bar to the minimization problem. And now the vector B is integer by hypothesis. So B transpose Y bar is some integer number. And so Z star is an integer number. And by the previous characterization of integral polyhedra, it tells you that your polyhedron is indeed integral. Okay, so now let's go back to the three questions that we asked. So we had this 4 sets of optimization problem. We were ordering the optimal value for each of those optimization problems. And then we were asking the following question. So let's look at the last question. When is it that Z ideal is equal to ZD for all non-negative integer vectors W? Well, this is just saying that the system mx smaller than or equal to 1, x non-negative, is TDI. Now let's look at the second condition. The second condition is just saying that x greater than or equal to 0, mx smaller than or equal to 1 is an integral polyhedron, right? So we're using the same characterization of integral polyhedra. If you optimize over a polyhedron using an integer objective function and you always get an integer value, then that polyhedron is integral. And finally, what is the condition 1 saying? Well, the condition 1 is really the intersection of all the matrices that are satisfying condition 2 and condition 3. Now, one thing that we will see in the next lecture is that integrality, in fact, implies total dual integrality in this particular case. So what does that tell you? Well, it tells you that 2 and 3 are really the same class, and therefore 1 is the same class as well. So all of those conditions are, in fact, equivalent. All of those questions are equivalent. So now we can introduce sort of the star of the show for the set packing problem. A 0, 1 matrix M is perfect if x non-negative, mx smaller than or equal to the vector of all 1 is integral. Now, one thing which is really surprising is that there's just a single combinatorial object which is associated with perfect matrices. Namely, we will show that a 0, 1 matrix is perfect if its maximal rows as a characteristic vector of stable sets of a perfect graph. Now, you don't need to know what those things are. We'll discuss those things later on. But the point is that there's just one object, one graph object, which is associated with perfect matrices. And so the study of perfect matrices really turns into the study of perfect graphs. So let us move on to the set covering problem now. And we're going to start with a classical min-max relation. So you're given a graph G with 2 special vertices, say S and T, where S is different from T. And you have the following min-max relationship. The size of the smallest ST cut, so with fewest number of edges, is equal to the maximum number of pairwise disjoint ST paths. So here we're talking about edge disjoint paths. So no 2 paths share an edge. So I can illustrate this on the following little example. You have 1 red path, 1 green path, and 1 blue path. They are pairwise edge disjoint, and you have an ST cut that contains exactly 3 edges. So what we would like to do is to restate this min-max relationship as a primal dual statement on integer programming. So let's move to an integer programming framework. We are now given a 0, 1 matrix. We're given some non-negative weight for the objective function. And we're defining the set covering integer program as minimize W transpose X, subject to mx greater than or equal to 1, and x is non-negative and integer. Now note that you can assume that in any optimal solution, or the variable x take either value 0 or 1. Okay, so why is this called set covering? Well, think of, again, the matrix M as representing sets. Every column is the characteristic vector of a particular set. So if you look at an optimal solution to your IP, right, you look at the corresponding column where you set those variables to 1. The constraint mx greater than or equal to 1 will tell you that you're looking for a family of sets that are covering the ground set, right? And so you're looking for a minimum weight family of set covering the ground set. All right, so this is our friend, our set covering problem there. And now we're going to define the LP relaxation. So we toss away the condition that x is integer. Then we write down the linear programming dual of that. We get our problem D. And then we add the condition that the variable y should take integer values. And we get our problem ID. Right? And now we can look at the optimal value for each of those different optimization problem, and we can try to compare those optimal values. So this is what I claim. So, well, ZIP is greater than or equal to ZP because, well, P is obtained by relaxing IP, and I'm now looking at a minimization problem. ZP is ZD because of strong duality, and ZD is greater than or equal to ZID because I'm now throwing in the condition that y is integer, and I'm looking at maximization problems here. All right, so now I want to go back to Mangers Theorem, and I'd like to restate this in that primal dual integer programming framework. So we will need a matrix M where the columns correspond to the edges of the graph, and the rows correspond to the characteristic vectors of ST paths, right? So for instance, here's a graph on the left. It has edges 1 through 5. So my matrix M has column 1 through 5. And I have a path 1, 3, 5. So I put 1 in position 1, 3, 5 for, say, row 1, for instance, and so on. All right, so if I take such a matrix, and I look at my integer program, so this is my set covering problem there. For the choice where W is the vector of all ones, what do I get? Well, let's just write down IP, right? So remember, I can assume that all the variables are either 0 or 1. So you can think of those variables which are 1 as telling you which edges that you're picking. And if you look at each of the rows of the matrix M, they correspond to characteristic vectors of ST path. So you're grabbing one edge from each of the ST paths. So what you'll end up doing is picking a set of edges which forms an ST cut. You'll pick a minimum set of edges because the costs are all 1. Right? So IP is looking for a minimum size ST cut. What does ID does, again, for the case when W is 1, well, we'll just write it down here. So now you have a variable y for every row of your matrix M, or equivalently for every ST path. And again, you can assume that y are going to be either 0s or 1. So you are essentially either selecting an ST path or you're not selecting it. And the condition, because you get this M transpose Y smaller than or equal to 1, the condition is that you do not pick two paths that overlap in one edge. So in other words, you're looking for a maximum number of disjoint ST paths. Right? So Mangers Theorem is just the statement that ZIP is ZID for the cost or cost vector of 1. So as an exercise, you should check that, in fact, ZIP is equal to ZID for every non-negative integer vectors. And in fact, it says something nice for graphs. It talks about undirected flows. So let's look again at those 4 optimization problems. So remember, the first one is just your set covering problem. Then you have the LP relaxation, its dual, and the integer version of the dual. So for each of those problems, you can look at the objective value for a particular W, and as we've seen, you always have the same ordering of values. ZIP is greater than or equal to ZP, which is equal to ZD by strong duality, which is greater than or equal to ZID. So you can ask the following question, right? So for what class of matrices do you have ZIP is equal to ZID for every non-negative integer W? For what class of matrices do you have ZIP is equal to ZP for every non-negative integer W? And finally, for what class of matrices do you have ZID is equal to ZD for every integer non-negative W? So we can use the machinery we've developed earlier. So the last question is equivalent to looking at the class of matrices for which the system mx greater than or equal to 1, x non-negative, is TDI. The second question is just looking at when the polyhedron x non-negative mx greater than or equal to 1 is integral. And the first question is really looking at matrices which are satisfying condition 2 and condition 3. All right, so this is what we have. All right, so we know that 3 implies 2. In other words, total dual integrality implies integrality of the associated polyhedron. So let's define Mi to be the class of matrices satisfying condition I. Right, so M1 is a set of all matrices for which ZIP is always equal to ZID, and so on. So what do we know? We know that M3 is a subset of M2, right? This is because total dual integrality implies integrality. And we have that M1 is the intersection of M2 and M3, therefore equal to M3. Right? So there are really sort of 2 classes, right? Really M2 and M1. So we're going to say that a matrix M is ideal if the associated polyhedron is integral. In other words, M is in M2. And we're going to say that M is Mangerian if the associated system of inequality is TDI. In other words, that M is in M1. Right? So 2 properties, idealness and the Mangerian. And so you could ask, well, what is the relationship between these properties? So if a matrix is Mangerian, then it's ideal, right? Remember, Mangerian means total dual integrality. Ideal means integrality of the polytope. So total dual integrality implies integrality. So Mangerian implies ideal. What about the converse? Well, the converse doesn't hold, and here's a matrix that we'll see many times. This is a matrix Q6. We'll see that it's ideal. It's actually not completely trivial to check that it's ideal. right? I mean, you have to check that the associated polyhedron is in fact integral. But we'll see several arguments of that. But it's easy to see that it's not Mangerian. So what is IP going to do? IP is going to look for a set of columns that are covering all the rows. Now you don't have columns of all 1, so ZIP is going to be greater than or equal to 2. And in fact, you could pick the first column and the last column, so ZIP is in fact equal to 2. What is ID doing? It's looking for a set of disjoint rows. There's no 2 disjoint rows, so ZID is going to be equal to 1. So you're going to have a gap between the value of the integer primal and the value of the integer dual. Now, one thing which is very different for ideal matrices and Mangerian matrices versus perfect matrices is that we have no single combinatorial object associated with those classes matrices. For perfect matrices, we will see that the study of perfect matrices is essentially the study of perfect graphs. But there are lots of very interesting and very different combinatorial objects that give rise to ideal matrices and Mangerian matrices. So it seems that those properties are inherently more complicated and more difficult to understand. So in the remainder of the course, we'll have one lecture on perfection. So I will show you that perfect matrices and perfect graph are just 2 ways of looking at the same object. And then we'll discuss idealness, so integrality of the polyhedron associated with the set covering problem. And then we'll discuss the Mangerian property, that min-max relationship